Welcome to Ask and Learn.
We want to sketch the graph y is equal to x minus 3 times the square root of x. So in this chapter, they give us this laundry list of steps we should follow. So let's just go ahead and follow those one by one. So the first thing they tell us to do is to look for our domain of our function. So we know that underneath the radical, we need this to be larger than or equal to 0. So that would just be x greater than or equal to 0, or 0 to infinity. And this should actually be including 0, since we can plug 0 in. So let me go ahead and fix that. So we have the bracket there, so we have our domain. The next thing they tell us to do is to look for our intercepts. So intercepts, well, not x-intercept, but just intercepts. Intercepts. So let's go ahead and first find our x-intercepts. So that's going to be where the function is just equal to 0. So x minus 3 is equal to the square root of x. So that tells us either 0 is equal to x minus 3, or 0 is equal to the square root of x. So that says x is equal to 3, x is equal to 0, and both of these are within our domain. Next, we can find our y-intercept, and actually we already know what our y-intercept is from here. So this tells us that's also our y-intercept. So we actually don't need to go about solving for that. Now, for symmetry, well, there really won't be any kind of periodicity within this, but we could possibly check to see if f of negative x works, to see if this is an even or odd function. But we run into the issue of when we do x minus 3, or negative x minus 3, and then square root of negative x. Well, if I try to plug in like 1 or 2, this part here is going to be undefined for our domain. Undefined for domain. So we really won't have any symmetry, or at least no symmetry about the origin or the y-axis. Now the next thing they tell us to look for is asymptotes. So we won't have any vertical asymptotes, but we can at least possibly check to see what our end behavior is going to be. So since we don't go to negative infinity, we can at least go ahead and check what happens as x goes to positive infinity. So limit as x goes to positive infinity of f of x. Well, x minus 3 is going to go to infinity, and the square root of x is also going to go to infinity. So we have that our end behavior here is just going to go towards infinity as x approaches infinity. The next thing they want us to do is to determine where our interval is increasing and decreasing, and I'm going to lump this in with the next step of finding our local maxes and mins. So to do that, we need to know what y prime is, so let's do that on another page. So let me first write y is going to be equal to, and I'm going to distribute the square root, and doing that is going to give x to the 3/2 minus 3x to the 1/2, and I'm just rewriting it with the power so I can apply power real quickly. So that's going to be y prime is equal to 3/2 x to the 1/2 minus 3 over 2 times x to the negative 1/2. And if you want, we can go ahead and combine those to get 3x minus 1 over 2 square roots of x. And I want to do this because now I can go ahead and set this equal to 0 to figure out our possible critical points. So nothing I plug into the denominator will ever make this equal to 0, so I just have x minus 1 is equal to 0, or x is equal to 1. So this is our possible point of inflection. Now, something else we would want to check is where our derivative is undefined for critical values, which would be x is equal to 0, But since that is our endpoint of our domain, we don't really need to go to check to see if that'll be a local min or max. But do keep in mind, normally we also need to check for where the function is undefined for critical values as well. Right. So y prime we found to be 3x minus 1 over 2 square roots of x. And so what we need to do is figure out where it's increasing, which would be where y prime is strictly larger than 0. So this is going to be from 1 to infinity. And we know the function is going to be decreasing when y prime is strictly less than 0, which is 0 to 1. Now we found that our possible point that could be a max or min is x is equal to 1. So to the left of x is equal to 1, the function is decreasing, and to the right of x is equal to 1, the function should be increasing. So that tells us this here is going to be a local minimum of our function. Right. The next thing they suggest that we do is to look for concavity and any kind of points of inflection we might have. So that means we need to look for y double prime. So y double prime is going to be equal to, now I'm going to go ahead and take the derivative of this because it's just power rule as opposed to when I used algebra to simplify it. So doing that is going to give 3/4 x to the negative 1/2, and then it's going to be plus 3/4, and then x to the negative 3/2. And now we can use a little bit of algebra here to rewrite this to get 3x plus 1 over 4x to the 3/2. So again, we're going to set this equal to 0. And that's going to tell us that x plus 1 is equal to 0 or x is equal to negative 1. Now, this would be a possible point of inflection, but this is not in our domain. So our domain, remember, was supposed to be 0 to infinity. So since this isn't in it, it won't be a possible point of inflection. So in this case, we will have no possible points of inflection. All right, so we had y double prime is equal to 3 over x plus 1 over 4x to the 3/2. And we will find that this function is concave up when y double prime is strictly larger than 0. And this just happens to be our entire domain. So for concave down, that's when y double prime is strictly less than 0, and there are no intervals for this. And like we said earlier, there are going to be no inflection points, since the only thing that would make our second derivative equal to 0 would be x is equal to negative 1, which is not in our domain. All right. Now that we've done that, they tell us we can go ahead and start graphing. So we have our intercepts at x is equal to 0 and x is equal to 3. We know at 1 we're going to have a minimum. And we know as x goes to infinity, the function should go to infinity. All right, so now that we have this, we can just go ahead and start connecting everything. So we're going to start from x is equal to 0. And we know to the right of x is equal to 0, the function is decreasing. So I'm going to decrease until I hit my first point, which is going to be x is equal to 1, which I should have a minimum there. And then after this, I need to hit my next important point, which is going to be x is equal to 3, and it's just going to go up like this. So this is our nice sketch of the graph. You could go back in and possibly say what this value is for our minimum, but since we're just trying to sketch it, I think this is all the relevant information we actually need.